Today we prove two facts. First, an operator cannot have more distinct eigenvalues than the dimension of the space. Second, every operator on a finite-dimensional non-zero complex vector space has at least one eigenvalue. Complex numbers are finally doing customer service. An operator means a linear map from a vector space back to itself. So T lives in L of V, meaning T maps V to V. An eigenvalue lambda comes with a non-zero eigenvector versus satisfying T versus equals lambda V. The vector may stretch, shrink, or flip, but it stays on its own line. Suppose T has m distinct eigenvalues. For each one, choose one non-zero eigenvector. The previous theorem says eigenvectors belonging to different eigenvalues are linearly independent. That one sentence is now doing heavy lifting. As it should. A linearly independent list in V cannot be longer than dim V, so M is at most dim V. That proves the first result. No operator can have infinitely many distinct eigenvalues inside a finite-dimensional space. Greed has limits, apparently. Now assume V is finite-dimensional, non-zero, and complex. We will prove every operator on V has an eigenvalue. The proof uses polynomials applied to operators. Yes. The polynomial detour was not decorative filler. Astonishing planning from mathematics. Let n be dim V and choose a non-zero vector V. Then the list V, T squared V, up through T to the n V, has n plus 1 vectors. In an n-dimensional space, n plus 1 vectors cannot be linearly independent, so we get a non-trivial linear combination equal to 0. Use those coefficients to build a polynomial P. Then the dependence relation says P of T applied to V is 0. This polynomial is not the zero polynomial. Also, its degree is positive, because if only the constant term survived, it would force a zero multiple of our non-zero versus nonsense. No thank you. Because we are over the complex numbers, the polynomial splits completely into linear factors. Now replace C by T. The equation P of T applied to versus equals 0 becomes a product of operators killing a non-zero vector. If all factors T minus lambda Ji were injective, then their product would be injective too. It could not send a non-zero vector to 0. Therefore one factor is not injective. So there is a non-zero U with T minus lambda Ji applied to U equals 0. That is exactly Tu equals lambda Ju. So lambda J is an eigenvalue. Every operator on a finite-dimensional non-zero complex vector space has one. Complex numbers finally paid the bill. The count result comes from linear independence. The existence result comes from making too many vectors, building a polynomial, and factoring it over the complex numbers. Next, eigenvalues will help us build upper triangular matrices. And then diagonalization will start looking less like magic and more like organized bookkeeping. Barely an improvement, but still.